Hi everyone. Today we're going to be talking about solubility. Okay, specifically the solubility of ionic solutions. Now in general, if I say what does it mean to be soluble, we mean it dissolves. Okay, and most of the time we mean in water. There are other solvents though that you will encounter. Okay, so if I dissolve some sugar in water, the sugar molecules, the sucrose molecules themselves, have lots of OH groups all over them. And those OH groups are going to be attracted to the water molecules through hydrogen bonding. And the random molecular motion of the water molecules is going to cause them to spread out throughout the whole beaker of the water. And that's the solute dissolving. Now, if it is an ionic substance, it can also dissociate. So what's the difference between them? Dissociating is breaking up into ions. For like NaCl solid breaks up into Na plus aqueous and Cl minus aqueous. Our old friend Svante Arrhenius first described this back in the 1880s. Okay? Now a solubility product is the KEQ expression for this happening. Okay? And what does it indicate? It tells you, okay, the concentration of dissolved ions in a saturated solution. So it's important to know a saturated solution is where you have an equilibrium between solid and dissolved solute in a solution. Okay? Now, we've actually just said that, why does the salt dissociate? It's polar. Water's polar. Water's polar. Like dissolves like, okay, etc., etc. And when it dissociates, it turns into ions, okay, positives and negatives. So, if I'm going to draw a picture then, here's a beaker, it's got water in it, must be a windy day, there's lots of waves. Na plus, Cl minus, there you go. They're separated, they're not attached to each other anymore, they're just floating around freely. Okay? That's because sodium chloride is soluble. Now, silver chloride is not. So what that means is I have my beaker of water, and then on the bottom of the beaker, I have a pile of solid AgCl. But wait, there's more. AgCl is not terribly soluble. It is going to dissociate to a very minor extent. So I will have some Ag pluses and some Cl minuses that float around in there. Okay? A tiny, tiny amount. And their concentrations would be represented by the solubility product, Ksp, which is just an equilibrium constant. Okay, now, what happens when I mix, actually, NaCl and AgNO3? First off, I have Ag plus, I have NO3 minus, I have Na plus, I have Cl minus. Okay? Now, when I mix them, I'm going to get a pile of AgCl precipitate at the bottom of this. I'm going to have lots of sodium ions and lots of nitrate ions. Now, I will have, to a very, very minor extent, a few Ag plus and Cl minus ions floating around in there. But they're not a predominant species. There's very few of them there. But still, there are some there. They do dissociate to some extent. Okay, so when I'm looking here at page 9, what I'm seeing is a table of KSPs. Don't memorize these, okay? Always provided for you. And you're going to notice that some of these are incredibly tiny numbers, okay? 10 to the negative 50ths, etc. Okay? So now, what's the molar solubility of AgCl in water? So AgCl, solid, breaks down into Ag plus Cl minus, which are both aqueous. ICE, ignore that because it's a solid. 0, 0. Now I could write plus X. It's just typically the AP exam uses the letter S. A lot of textbooks use S also. S stands for solubility. Okay? Now the Ksp for this is equal to the Ag plus times the Cl minus, which equals, I look it up in the table, okay, silver chloride 1.6 times 10 to the negative 10th. So S squared is 1.6 times 10 to the negative 10th, or S equals 1.3 times 10 to the negative 5th molar. Now, that actually tells me a lot. There's some really valuable information there. It tells me how many moles of AgCl will dissolve per liter. It tells me what the concentration is of the silver ion. It tells me what the concentration is of the chloride ion. And those can be used in other types of questions also. All right. Now, what's the molar solubility of PbF2 in water? Well, slightly different ratio. So it'll be slightly different math, but the same basic idea. ICE, ignore that because it's a solid. 0, 0, plus S, plus 2S. So I have S and I have 2S when I add those together. So Ksp equals the concentration of Pb2 plus times the concentration of F minus quantity squared. Look that one up in the table, 3.7 times 10 to the negative 8th. Now this is S, and this is 2S, but it's squared, so that's 4S cubed, which equals 3.7 times 10 to the negative 8th. Now, KSPs usually just take one of three forms. S squared, 4S cubed, or 27S to the fourth, just depending upon how many ions are present. 2 ions, 3 ions, 4 ions. Okay? If you know those three, you're set for pretty much all the questions you're going to encounter. So I can solve this pretty easily on a calculator. S equals 0.0021 molar. And I can use that number to figure out how many moles of this dissociate, or what's the concentration of Pb2 plus, or what's the concentration F minus. There's a lot that I can do with that. Okay, let's leave that on screen for you for a minute. Okay. Now, let's do a slightly different problem that is maybe more useful in the real world. What's the solubility of CaCO3 in water? Now, I didn't say molar, did I? I just said solubility. So we're going to answer in grams per liter. So CaCO3 solid breaks down. I get Ca2 plus, I get CO3 2 minus, aqueous, aqueous, ICE, ignore, 0, 0, plus S, S and S. Ksp equals the concentration of Ca2 plus times CO3 2 minus. I looked that up. I got 8.7 times 10 to the minus 9th. So S squared equals 8.7 times 10 to the minus 9th, or S equals 9.3 times 10 to the negative 5th, and that's in moles per liter. Now, the molar mass of calcium carbonate is 100. So I'm going to multiply this by 100.09 grams per mole. The moles cancel, and I add 9.3 times 10 to the negative third grams per liter. So that tells me how many grams of something can dissolve in 1 liter of distilled water. That's a good skill to have. Now for copper bromide, CuBr. What if I already know the solubility? Can I find Ksp? Sure. Cu plus Br minus. Okay, I could do an icebox if I wanted to. 0, 0, plus S, S and S. So Ksp equals S squared, which equals 2.0 times 10 to the negative 4th squared, because the solubility is S. And that equals 4.0 times 10 to the negative 8. All right, so those are your typical questions for dissolving something in water. What if you're not dissolving it in water? What if you're dissolving it in another solution? Like let's dissolve AgCl in 0.1 molar NaCl. Okay. AgCl breaks down, that's a solid, into Ag plus aqueous and Cl minus aqueous. Do an icebox, ICE. Ignore. 0. And here's the difference. 0.10, because I already have chloride ions. Plus S, S, 0.10 plus S. So Ksp equals, and I'm going to have S multiplied by 0.10 plus S, which equals 1.6 times 10 to the negative 10th. That's like the 1 Ksp, I remember. You'd look it up in the table where it would be given. Now, this could be a complicated quadratic if I wasn't careful. But since this is such a small number, I know that that S is essentially going to be 0 compared to 0.10. I'll just approximate it away. 10 equals 1.6 times 10 to the negative 10, or S equals 1.6 times 10 to the minus 9. Now, I chose that specific compound for a reason. If I come back to page 1, I see that the regular solubility, just in water, of HECl is 1.3 times 10 to the negative 5th. So here, if I'm trying to dissolve it in NaCl, it is 10,000 times less soluble. That's a big deal. That's a big difference. And it can all be explained by Le Chatelier's principle. So, do the same thing for PBF2. We're going to put in 0.10 molar NaF. ICE, ignore this, 0.10 plus S plus 2S, S 0.10 plus 2S. So my Ksp equals S times 0.10 plus 2S squared equals 3.7 times 10 to the negative 8th. Okay, wow. That could be an ugly cubic equation. So I'm going to approximate that away and basically get S over 0.10 squared equals 3.7 times 10 to the negative 8, or S equals 3.7 times 10 to the negative 6th. Now, to compare back, when it was just in distilled water, it was 2.1 times 10 to the negative 3rd. So this is really 1,000 times less soluble again because of Le Chatelier's principle and that common ion. This is the common ion effect. Okay, so what was the physical meaning of Ksp? A saturated solution. What is a saturated solution? One where there is an equilibrium between undissolved solvent and dissolved solvent in the beaker. So, Q equals Ksp means you have a saturated solution. Back to our reaction quotient. If Q is greater than Ksp, I have too many product ions. That means with more ions than you can have dissolved, we're going to get a precipitate. You have more ions than can be dissolved. Q is less than Ksp, no precipitate, because you don't have enough ions to represent a saturated solution. All right. Pop up to page number 11. We're going to calculate some Qs. If I mix copper nitrate and Ki, CuI is my likely precipitate. Okay? So to calculate Q, which equals the concentration of Cu plus times the concentration of I minus, I have to figure out what the dilution here is. 100 milliliters and 100 milliliters added together is 200 milliliters. And notice both concentrations are the same. I'm going to cut those concentrations in half. So my concentration of CO2 plus is now 5.0 times 10 to the negative 4, because I divided that by 2, and it's also equals the I minus. So Q equals 5.0 times 10 to the negative 4th quantity squared, which is going to be 2.5 times 10 to the negative 7th. So let's see, 25 times 10 to the negative 8th, so 2.5 times 10 to the negative 7th. Yep, did that right. So now I go and I look up the Ksp value for this. And the Ksp for it is 5.1 times 10 to the negative 12. Wow, huge. Lots more precipitates. Okay. Now, I'm going to mix 500 milliliters of calcium nitrate, 500 milliliters of sodium chloride, so CaF2 is my potential precipitate. Okay? So I have to calculate its Q. 500 and 500 again, I'm cutting these concentrations in half. So the concentration of calcium ion is going to be 1.5 times 10 to the negative 6th. And the concentration of F minus will be 1.0 times 10 to the negative 6th. So my Q equals the concentration of Ca2 plus times F minus squared, which equals 1.5 times 10 to the negative 6th multiplied by 1.0 times 10 to the negative 6th squared. So that's 1.0 times 10 to the negative 12th, 1.5 times 10 to the negative 18th. Yep. Okay. Now I look up the Ksp, 4.0. That's negative 18th, sorry. 4.0 times 10 to the negative 11th is the Ksp. Oh, infinitely smaller, so no precipitate. Okay. Now, I find the next two questions pretty interesting because they connect pH and solubility. So FeOH sub 2 breaks down into Fe2 plus and 2OH minus. They do a nice box. All right. Now my hydroxide ion concentration can be determined. If the pH equals 9.50, the pOH equals 4.50, so the hydroxide is 10 to the negative 4.50. So since that's a 0.5, this is a 3.16 times 10 to the negative, okay, let me get this right. So that's 10 to the negative 4. That's going to be negative 5th. Okay, that's the hydroxide ion concentration. So that means that's 2S. So S equals 1.58 times 10 to the negative 5th. The Ksp for this is a 4S cubed which is 4 times 1.58 times 10 to the negative 5th cubed, and that equals 1.6 times 10 to the negative 14th. So both solubility and the value of Ksp. And they happen to match what's in the table up front, so that's always cool. So for silver hydroxide, AgOH breaks down into Ag plus OH minus, ICE, ignore, 0, 0, plus S, S and S. S squared equals. So I went back a few pages, I looked up the Ksp, and it's 1.5 times 10 to the negative 8th. So S equals 1.22 times 10 to the negative 4th. So the POH is the negative log of 1.22 times 10 to the negative 4th, and that equals 3.91. So then the pH is a 10.09. Okay. Now, I sort of lied to you. I think it's forgivable. But is the hydroxide really 0? No. In distilled water, it's about 10 to the negative 7th. I don't think it's going to affect things too much by not putting it here, but I wanted to point that out to you. Okay, so here are some thinking questions, and I intended the lecture to actually make you go home and think about these. I wasn't going to answer them directly. I have a saturated solution of PbCl2. I add one more drop of PbCl2 solution to it. What happens? It precipitates, because I have now more than a saturated solution. Okay? Now, I've got a 1 liter flask and I've got a 2 liter flask of saturated PbI2. Which one has more moles of Pb2+? That's the 2.0 liter. We know that molarity equals moles over volume, so moles equals molarity times volume. Now, the molarity of the Pb2+ is the same in both because it's saturated. I could figure that out, with an icebox. So all that's changing here is the volume. 1 times a number, 2 times the same number, 2 times it is your answer. So now, what if I have a 1 liter flask and a 2 liter flask with saturated PbI2? Which has the higher concentration of Pb2+? Neither. We just said they both have the same concentration because they're both saturated. Okay, that's our little tour through solubility. Hope that helps. This is Morgan, signing off.